This video will focus on how to mathematically solve KSP problems. What I have on the screen right now is a general flow for how I go through all KSP problems, and they're very similar to how I would do a KEQ or a KP type problem. So number one, you have to make sure you have a complete and balanced chemical equation. For KSPs, that means a dissociation equation. So you have a solid ionic compound dissociating into its ions. Number two, you need to write the K expression, write the KSP expression, which will equal the concentration of each of the ions raised to a power of its coefficient, just like normal for Ks. Then we determine relative values and fill in any information that's presented, similar to how we would do an ICE problem, and then we solve. On the worksheet I made for KSP practice, essentially there are 3 example problems, and so that's what I'm going to go through. So if you have that worksheet available, it wouldn't be a bad idea to kind of take notes on that in terms of the process of how to solve. So the first problem here gives you information about how much lead iodide, PbI2, can dissolve into 1 liter at a certain temperature and asks you to solve for the KSP. So the first thing to do for these problems, again, is to write your dissociation equation and then also your K expression. So when it comes to PbI2, it dissociates into the cation of lead and the anion of iodine. Again, iodine's a diatomic, but as an aqueous ion, so those are both aqueous ions, it's not a diatomic. We just have 2 of those -1 ions. Now, if I read the problem, I get one number. I get that 1.2 times 10 to the -3 moles of lead iodide can dissolve into a whole liter. So if you think about that in relation to this equilibrium, essentially initially, I'm putting in 1.2 times 10 to the -3 moles per liter, so that's molarity, in. And at the beginning, none of it has dissociated. Okay. Over time, and essentially if you understand equilibrium in relation to dissolving, at saturation, at this point where all of it has dissolved, I now have none of this left, and all of it has gone to be the product. So what I know then about my change is that I had to go down by this amount to make it so that I had none left once I have a saturated solution. Now, as always with the change, it's all about the stoichiometric coefficients. So this is a 1 to 1 to 2 relationship. So if all of this becomes product, then I make 1.2 times 10 to the -3 of this lead ion also, but I make 2 times that amount of iodine to keep a 1 to 1 to 2 relationship, which is 0.0024. Then again, equilibrium, 0 plus this will be the same, 0 plus this will be the same, and that's now what we plug into our equilibrium expression. So to figure out the K for this solubility product constant, I take the concentration of the one ion and the concentration of the other ion. Now this is squared because that's the rule for K expressions. We raise them to a power of their coefficients. So now to solve this K, I just plug in and solve, and the KSP for this lead iodide is pretty small, right? That's not a lot of dissolving, but that's the relationship. So this is how we solve a problem. If I tell you how much of my salt essentially can dissolve, then it's a question of saying, well, all of that became product. What is the stoichiometric ratio of the ions? Plug them into the KSP and solve. Example problem number 2 now, I give you the KSP and ask you to calculate the concentrations of the ions when I'm saturated. So again, I write my dissociation equation, and my K expression is the concentration of the 2 ions. Neither one has a coefficient, so I'm no raising to a power. I know my K. My K is 1.8 times 10 to the -10. But essentially here I have 2 variables, and that makes it hard to solve. But you know something about those 2 variables, okay? If initially the amount I put in and allowed to dissociate was X, then we know the change is that it went down by X, okay? Now, based on the change, I need a 1 to 1 to 1 relationship, so then these both go up by X. So essentially this is just x squared because they both have the same concentrations. When this thing dissociates, you get 1 silver per 1 silver chloride and 1 chloride per 1 silver chloride. So we have a 1-to-1 relationship. So now I can just solve for x, and that would be the concentration of each ion since they're the same. So I'm just going to take the square root of this side, which then ends up being this number. And because I was solving for these concentrations, that now is a molarity value. So essentially, we're using this concept still of the stoichiometric proportions to say that depending on what their ratios are, we can figure out how they relate to one another as they dissolve. For this last example problem here then, we're being asked to calculate the molar solubility of the silver chromate. And again, step 1, I'm going to create my dissociation equation, and step 2, I'll create my K expression, where it's a concentration of silver squared times the concentration of that chromate ion. Okay. So for this problem, it's slightly difficult just because you don't necessarily know what the problem's asking for most people. When they read it, they say molar solubility of silver chromate. I don't know what they're asking me to solve for. Essentially, what we're asking you to solve for is when this dissolves, what's the max amount of concentration, molar, that we can put in of the salts to make it saturated. So molar solubility is the max amount of this that can go in to make ions before it becomes excess on the bottom. So we're calculating that moment where the ions multiplied together equals K. Okay? So essentially what I would say for molar solubility usually is what I'm trying to actually solve for is this. How much can I initially put in so that over time all of it becomes ions and there's nothing left? Okay, so that's what we're solving for. So usually I define that as my x. So initially, as we've already seen, I'm going to put that salt in. It won't have dissociated yet. Then the change is it's going to go away and it's going to produce those ions at a 1-to-2-to-1 ratio based on this dissociation equation. So this silver is going to go up by 2x. So for every 1 silver chromate that dissociates, you get 2 silvers out. And for every 1 silver chromate dissociates, you get 1 chromate out. So now at equilibrium, I don't have any more of this. And I have 2x of this and just x of that. Looking at the problem, I give you the KSP value, so you can plug that right in. And then I plug in how I've set up my x's, so it's going to be 2x squared times x. 2x squared now is 4x squared, and that's still multiplied by x, so this whole side is 4x cubed. So to solve that, I'm going to divide by 4 and take the cube root. If I do that, I end up getting 6.5 times 10 to the negative 5, and that's a concentration because I'm solving for one of these brackets. The question is that the answer to my problem? Okay, is that the molar solubility? Once again, what molar solubility is the amount we can put in that when dissolved is the K, right? This is the max that can dissolve, the solubility product constant. Because we defined our x as that value and then we solved for x down here, this is absolutely our answer. Okay? So molar solubility and like ion concentrations can be the same value. It's just a question of what you're comparing. So this is also the amount of concentration that the chromate ion creates, but not the silver ion because it's 2 times that x value. So those are the 3 main types of problems. Again, if I'm asking you to solve for the molar solubility or the solubility, we're asking you to solve for essentially this, which if you define as x is easier to answer. The only other sticking point for many people is the fact that in the end it's 2x squared. They feel like I'm doing double duty for this 2. Understand that this squared up here is because that's the definition of a K expression. You must raise it always to a power of its coefficient. Where this 2 right here is based on stoichiometric proportions of this reaction actually being carried out. So they're happening because of the same reason, because there's a 2 there, but they're being applied for 2 completely different reasons. One is an equilibrium concept, and one is a stoichiometric reaction concept. So they're different executions, and so you're going to find this happen every time. Like if this was a cube situation, this would probably be a 3x cubed. Okay, so there is a relationship here that you'll just have to get used to. So go ahead and try to practice some of the problems. The answer key's online. Have a nice night.